Today I'm going to be talking about spatial and temporal discretization techniques for partial differential equations. Discretization refers to the way in which we split up or partition our domain of interest for numerical analysis. Two of the most commonly used spatial discretization techniques for solving partial differential equations are the finite difference method and the finite element method. The finite difference method spatially discretizes the partial differential equation using finite difference approximations of the derivatives involved. First, our domain of interest is subdivided into a grid called the finite difference mesh. This can be either uniform, with the grid length separating each node equivalent to step sizes of our choice, or non-uniform. Then, finite difference approximations are substituted for the partial derivatives. This creates a system of simultaneous linear algebraic equations with which we can solve for the interior nodes. The finite element method spatially discretizes the partial differential equation by subdividing our domain of interest into contiguous subdomains so that no vertex, or corner, lies on the edge of another subdomain. As a result, vertices will only coincide with other vertices, creating our nodes. Each node has a basis function. The partial differential equation is represented using variational formulations of the original equation. Along the time coordinate, our options for discretization schemes are as follows. We have the explicit scheme, the implicit scheme, and the semi-implicit scheme. The explicit scheme is based on the Euler forward finite differencing method and is considered conditionally stable. If the spacings are not properly chosen, the truncation error quickly amplifies for the explicit scheme. For a time step h, the upper bound of the truncation error varies with h squared. The implicit scheme, based on the Euler backward finite differencing method, is unconditionally stable. This means that the numerical solution is always stable. However, the truncation error for this scheme varies directly with h. The explicit and implicit schemes can be weighted and combined to create a semi-implicit scheme. The Crank-Nicolson scheme is a specific version of this method where both schemes are equally weighted and averaged. This scheme is second-order accurate in both time and space.